Feeling that pre-exam pressure for your operating system scores? Yeah, I get it, but you're in the right place. In the next few minutes, we're going to cut through all the noise, break down the trickiest concepts from Units 4, 5, and 6, and give you that shot of confidence you need to walk in there and just ace that test.
Look, from the nitty-gritty of disk scheduling all the way up to the big-picture architecture of Linux, there is a lot to cover. But don't you worry. Think of this as your personal crash course, designed to pinpoint the absolute essentials you have to know. So here's the game plan. We'll kick things off with Unit 4, all about how the OS talks to your disk drive. Then we'll build right on top of that with Unit 5 to see how it organizes all your data into files and folders. And finally, we'll put it all together in Unit 6 with a look at the Linux OS. Then, we'll wrap it all up with a super fast review to make sure it all sticks. Ready? Let's dive in.
Okay, so think about your OS as this super smart librarian, and your hard disk is a gigantic library. I/O management is basically the system that librarian uses to find the exact book you want instantly among millions of others. And this is where disk scheduling becomes absolutely crucial. It's all about minimizing the time it takes to grab that data, which is what makes your computer feel snappy and fast. To really get how we can speed up a disk, we've got to break down what access time even means. Now, transfer time and rotational latency, those are pretty much set by the physical hardware. You can't change them much. But seek time, that's the one. Think of a record player, right? Seek time is how long it takes to move the needle to the right groove. That's the part the OS can control, and that's where the magic happens. The whole game is about making that physical movement as small as possible.
So, here it is, a classic problem you'll probably see on an exam. The OS gets this list of requests, all wanting different tracks on the disk, and they're arriving in this exact order. Now the big question is, how do you handle these requests to minimize all that slow, physical movement of the disk arm? Let's check out the most common ways to solve this puzzle.
All right, first up is the most obvious approach. First come, first served, or FCFS. It's exactly what it sounds like. Like a line at the bank. First person in line gets served first. No exceptions. It's fair, it's simple to understand, but it's not very smart. It doesn't do any optimization at all.
So let's say our disk head is sitting at track 50. You can see the problem right away. We go from 50 to 55. Okay, then to 58. Still good. But then, bam, we have to jump all the way back to 39, then over to 18. Later on, we swing way out to 160, only to race all the way back to 38. It's pure chaos. It's like a delivery driver just zigzagging all over town. Sure, the packages get delivered, but it's a huge waste of time and energy. It works, but man, is it inefficient.
Okay, so let's get a little smarter with shortest seek time first, or SSTF. This one is all about being greedy, in a good way. From wherever the disk arm is, it just looks at the queue and picks the request that's closest. The goal is to make the smallest possible move every single time. Now there is a catch. What if a request is really far away? Well, it could get ignored for a long time as closer requests keep jumping the line. And this is a classic problem you need to know for your exam. It's called starvation.
Now, let's use SSTF on that same queue, starting at track 50. We go to 55, then 58. Okay, from 58, what's closest? It's 39, then 38, then 18. See what's happening here? We're cleaning up all the requests in one neighborhood before we make any big jumps. The total head movement is just dramatically lower than that crazy FCFS zigzag. The result? A way faster system.
And finally, we have the SCAN algorithm. Now, this is where things get really elegant. You'll probably hear it called the elevator algorithm, and that's the perfect way to think about it. The disk arm acts just like an elevator. It starts at the bottom, sweeps all the way to the top, and services every single request along the way. Once it hits the top floor, it reverses and does the exact same thing on the way down. This is an awesome balance of speed and fairness because it prevents that starvation we saw with SSTF. You know the elevator is eventually going to get to your floor, right? Same idea.
Okay, we've nailed how the OS physically gets data from the disk, but how does it organize all those ones and zeros into the neat files and folders we use every day? Well, that's the job of the file system. Ever actually stop to wonder what happens when you hit save? Let's pull back the curtain.
So at the heart of it all, you've got two things, files and directories. A file is just a single document, like a photo or an essay. A directory, or what we usually call a folder, is basically the filing cabinet where you organize all those documents. The OS gives us all the tools we need to create, delete, and manage this stuff,
which keeps our digital lives from being a total mess. But this leads to a really big question for anyone designing an operating system. A single file can be huge, made up of thousands of little disk blocks. So how should the OS actually arrange those blocks on the physical disk? And this isn't just some minor detail. It's a massive design choice that makes the difference between a system that feels lightning fast and one that feels sluggish and slow.
Let's break down the 3 main ways to do it. First, you have contiguous allocation. This is where all the file's blocks are stored together in one long line. Super fast for reading a file from start to finish. The problem? You get a lot of wasted space called external fragmentation. So think fast but wasteful. Next is linked allocation. Here, blocks can be scattered all over the disk, and each one has a little pointer to the next one in the chain. It's super flexible, but trying to jump to the middle of a big file? Forget about it. It's really slow. So think flexible but slow. And finally, there's indexed allocation. This is a really clever compromise. You have a special index block that's like a table of contents for the file, with pointers to all the data blocks. This gives us fast access without the fragmentation, but it does cost you a little bit of space for that index block itself. It's all about trade-offs.
All right, enough theory. Let's see how all these ideas come to life in a real-world operating system that pretty much runs the modern world, Linux. Seriously, it's on your phone, it's on web servers, it's everywhere. Understanding how it works isn't just for your exam. It's key to understanding how modern computers actually work.
So what's the big deal with Linux? It really comes down to these core features. It was built from the ground up to be multi-user, so lots of people can use the same machine at once. It's a powerhouse at multitasking, letting you run tons of apps at the same time without breaking a sweat. It's incredibly portable, running on everything from tiny smartwatches to the world's fastest supercomputers. The security model is legendary, with super tight control over who can see and touch what. And of course, it's open source, meaning anyone can see and contribute to the code. And that leads us to one of its coolest features, its file system.
The Linux file system is organized like a giant upside-down tree. And at the very top of that tree is one single directory called root, which is just represented by a /. Everything, and I mean everything on the entire system, lives somewhere under this single root directory. It's organized into standard folders like /bin for programs, /etc for config files, and /home for your personal stuff. It's just a simple, powerful, and really clean way to organize an entire system.
And we're at the finish line. We have covered a ton of ground, from the tiny movements of a disk head to the huge structure of a file system. So let's do a quick, final review of the biggest takeaways to lock all this in your brain so you can walk into that exam feeling totally prepared. If you remember nothing else, remember these 3 things. 1. Disk scheduling is all about one goal: minimizing physical seek time to make things faster. 2. The 3 file allocation methods, contiguous, linked, and indexed, are all about the fundamental trade-off between speed and using space efficiently. And 3. Linux is that powerful multi-user, multitasking OS that's defined by its single tree-like file system that starts at the root /. Got it?
And that is it. You just powered through the core concepts of 3 major OS units. You've done the work, you understand the ideas, and you are ready for this. Just take a deep breath, walk in there with confidence, and show them what you know. You've totally got this. Good luck!